All right, so continuing chapter 17, we're going to look at an example to find a confidence interval. Now, this is actually very easy with the TI calculator. So we need a 95% confidence interval here. We have our sample size, we have our sample mean, and then we have our sample standard deviation. And so the calculator will actually do all of this for you. So all you need to do on your TI 8384 calculator is go to stat. Let's go over to test. So just like we did with the confidence interval in the last chapter. And then we're going to go down to T interval. And when you get to that, the first line you see says input, and then we have data, and then we have stats. And you want to select stats. And when you select stats, you will see that we have X bar and X bar, again, and Y bar. You can interchangeable, either one is fine. So that, of course, is your sample mean. So you put the 0.0913. Next, you have your SX, which is S, and that is 0.0495. And then we're going to have our N, 150, and then the C level, of course, is 95. And then we calculate, and we should get 0.083 and 0.099. So very easy. And with like most things on the calculator, you want to do this enough to where you don't have to think about where to go to do this calculation. You certainly don't want to be taking the test and have to think about what command are you supposed to use to find a confidence interval, or to find where's the binomial PDF, that kind of thing. So certainly practice this enough that you can easily find those without thinking, because that problems like this should be fairly easy to get the points on. So thoughts about T and Z, or Z and T. So Z, of course, is talking about the normal distribution. So the student's T distribution, it is unimodal, it is symmetric about the mean, it is bell-shaped. In fact, if you just look at a T histogram, you would not know if it was a T histogram or a normal histogram unless it was stated. They look the same, basically. As degrees of freedom increase, it looks more and more normal. We could also say as sample size increases, because degrees of freedom is n-1. So as sample size increases, it looks more and more normal. And here's the important part. So this is needed because we're using S as an estimate for sigma. In other words, we don't know sigma. So let's mention that we don't know sigma. And in fact, if you do know sigma, then you should use normal CDF, the normal model, not T model. So that out of this section, that one is probably the most important. So make sure that if you do know sigma, you would use a normal distribution. So assumptions and conditions. So independence, randomization condition, the data should come from a random sample. And then the normal population assumption. So either the distribution is unimodal and symmetric on its own as a population, or you can consider sample sizes. And of course, these are guidelines, basic guidelines. But if you have a smaller sample, less than 15, then the population probably should be normal if you're going to do these things, do these methods for solving a problem. If you're between 15 and 40, it works well as long as the data are unimodal and reasonably symmetric. And then if the sample size is greater than 40, then it's pretty much works all the time, unless it's extremely skewed, like the CEO example. Although that one actually did work out, but we had to get a very large sample, so I don't think 40 would have cut it for that one. So the rule of thumb: the larger the sample size is, the better the T distribution works. So let's talk about confidence intervals and interpreting confidence intervals. So let's go back to, we used this example, similar example, because it's categorical in chapter 16. where we looked at premature babies, but let's just talk about all babies born in 1998. Found the sample mean, and then we got a confidence interval, 3364 to 3633 grams. And the proper way to interpret that, I am 90% confident that the interval from that to that contains the true mean birth weight. So again, we're trying to, we are given or we find X bar, and we want to estimate mu. And again, sample mean, population mean. So let's look at some wrong ways to interpret this. So 90% of all babies weigh between 3364 and 3633 grams at birth. The confidence interval is about the mean birth weight, not all babies. So the all babies here is kind of the bad part, because birth weights, you don't know that 90% are between those two, because they could be more spread out, and in which case the mean could still be in there. The sample mean could still be what it is, but it's just we have more low weight babies versus more heavier babies. So it's not about individual babies that we're trying. Always remember, just keep this in mind. We're estimating the population mean. We are 90% confident that a randomly selected baby will weigh between those two weights. Again, we're not looking at individual babies. We're looking at the mean birth weight of all babies. So the average of all of the babies that were born that year. The mean birth weight is 3498, which that would be the sample mean. That'd be halfway between these two. The mean birth weight is 3498.7 grams 90% of the time. So the population mean never changes. So the birth weight of babies born in 1998 is what it is not changing. And you assume that the population parameter, whatever that is, you assume is not changing. Obviously, it could possibly change. The average human height has changed over time. Back in the 1800s, it was a lot shorter than it is now. But generally speaking, we just assume the population mean is not changing. It is what it is, and we're getting a sample to try to estimate that. And like we talked about last time, the sample means will vary. So if you take one sample and you get 3498, you may take another sample and get 3458 or something. Some other, we'll probably get some other number. 90% of all samples will have a mean birth weight between those two numbers. This interval does not set the standard for all other intervals. Your sample mean is no more likely to be correct than any other sample mean. So as long as you do yours correctly and that next person does theirs correctly, either one is a reasonable estimate for where the population is. So kind of read through these a few times and read through the ones that we did in the last chapter. And it's a good idea to know exactly what you should say, and then it's easier to find out what's wrong with the wrong things to say. So, and we spend a lot of time on this because, again, like I said in the last chapter, we want you to be able to interpret this data, not just use a calculator and get confidence intervals. That's not that useful. It's more useful to be able to interpret the data. So if you have any questions, feel free to shoot me an email.